ഹലോ എവ്രി വൺ, വെൽക്കം ടു വിന്നേഴ്സ് ക്ലാസ് റൂം. ഞാൻ രമ്യ. വിന്നേഴ്സ് ക്ലാസ് റൂം എന്ന ചാനലിലെ ക്ലാസ്സുകൾ നിങ്ങൾക്ക് ഇഷ്ടപ്പെടുന്നെങ്കിൽ ഈ ചാനൽ സബ്സ്ക്രൈബ് ചെയ്തതിനെ സപ്പോർട്ട് ചെയ്യുക. അതുപോലെ ഈ ക്ലാസ് നിങ്ങൾക്ക് ഇഷ്ടപ്പെടുന്നെങ്കിൽ ലൈക്ക് ചെയ്യാനും ഷെയർ ചെയ്യാനും മറക്കരുത്. This is our first question. Through this video we are going to discuss all problems from exercise 1.1, real numbers. Okay? Use Euclid's division algorithm to find the HCF of 135 and 225. This is first part of first question. Okay, 135 and 225. Bigger one is 225. So we will divide 225 by the smaller one, that is 135. Okay, we know there is only 135 in 225, right? Okay, let us subtract now. Here 0, here 9, right? Only this much. Now what we will do, we will take this number here, 135. Okay, 135 is divided by 90. 90 plus 90 is 180, right? So we know there is only 190 in 135. Then subtraction, we got 45. Then what we will do, we will take this 90 here. See, 90 is divided by 45. We know 2 times 45 is 90, right? 45 plus 45 will get 90. So 2 times 45 is 90. We will get the remainder as 0. So what is the HCF here? Here HCF is 45. So here HCF of 135 and 225 is equal to 45. This is the second part of that question. Okay, using Euclid's division algorithm, we have to find the HCF of 196 and 38,220. Okay, we will take the bigger number here and we will divide it by the smaller one, 196. Okay, let us add 196 two times. What we will get? Right, 392. See, here we have 382. Okay, so we will take only 1 times 196. Okay, we will divide and we will subtract here 6 times, here 8 and here 1. Then what we will do, we have to continue this division process, right? Okay, so we don't know the multiplication table of 196. So for that I have added 196 this time. See, here what is the next number we have to consider? 1862, right? 1862. See, here I have added 196 continuously. Finally I got 1764. Obviously we know that if we add one more 196 here, it will exceed this 1862, right? So I am taking this number here, 1764. How many 196 are here? 1, 2, 3, 4, 5, 6, 7, 8, 9. See, 9 times I have taken 196 means here I have to write 9. Then again subtraction. Here 8, 9. And this 0 will come here. Okay, 980. See, 980 is here. How many 196 are there before 980? 1, 2, 3, 4, 5. So 5 times 196 we will get 980. Okay, now what we have to do next? You are calculating the HCF. See, here when this bigger number was divided by this one, we got 0 as the remainder. What does that mean? 38220 is equal to 196 into 195. Okay, so HCF of 196 38220 is 196 itself. See what happens here? This bigger number is a multiple of this smaller one. Bigger number is a multiple of this one. That means the highest common factor is 196 itself. This is the third part of first question. Here the biggest number is 867. We have to divide it by the smallest one. Okay. Now 255 plus 255. That means 255 into 2. 10, 11, 5. 5, 10. Again I am going to add 255 here. Okay. I think this is the easiest way of division. See, we don't know the multiplication table and all for all these bigger numbers, no? Then better you do it like this, adding it continuously. See, I got 765. Okay, it is suitable. Okay, I chose it. How many 255s? 3, right? So 3 times. Then we will do what? Subtraction. Here 2, 0 and 1. Then here division is over, but the remainder is 102. Then we will take this 255 here and we will divide it by 102. You know 2 times 102 means 204. That is enough. Okay, here 1 and here 5. Then we will divide this 102 by 51. We know 2 times 51 is 102. Thus we got the remainder 0. Which is the HCF here? 51. So HCF of 867 and 255 is 51. This is our second question. Show that any positive odd integer is of the form 6q plus 1, 6q plus 3 or 6q plus 5 where q is some integer. Okay. First let us assume a is an odd integer. Okay, we will start like that. A is an odd integer. Then we are going to divide a by 6. Why we chose 6 here? See, in the question, see here 6q plus 1, 6q plus 3 and 6q plus 5. That is why we choose 6 here. We are going to divide this a by 6. A is an odd integer. Anyways, by division we will get a quotient here. Okay, a quotient will be there and we will get reminders as 0, 1, 2, 3, 4 or 5. See, when I divide a number by 6, these are the possible reminders. If you have any confusions, you just listen here. I am going to divide 10 by 3. Okay, if you don't have any confusions, you can skip it. Okay, see here I have taken the number 10 and 3. 10 by 3 means 3 times 3, 9 and remainder 1. Okay, again I am going to divide 15 by 7. 2 times 7 is 14 and remainder 1. Okay, next I am going to take 19 divided by 7. 2 times 14, remainder 5. See, remainder is bigger one here, 5. But still, check it. 5 is less than 7, right? That means when we divide a number by another number, the remainder will never exceed the divisor. The remainder will never exceed the divisor. Okay? That is why we wrote it like this. Remainders can be 0, 1, 2, 3, 4, 5. That means below 6. Any number below 6 can be the remainder. Okay? And we can now represent A as 6q plus 0. Or A can be represented as 6q plus 1. See? When remainder is 1, we can represent it as 6q plus 1. When remainder is 0, we can represent it as 6q plus 0. Or A can be taken as 6q plus 2. That means remainder is 2. Or we can take A as 6q plus 3, where remainder is 3, like that. A can be taken as 6q plus 4. Or it can be taken as 6q plus 5. Okay, finished. All these reminders we taken into our consideration, right? Anyways, from here we get A is equal to 6q. Okay? 6q plus 0 is 6q. Now what is 6q? Actually, A is equal to 2 into 3q, right? 6q can be splitted like this, 2 into 3q. What does that mean? 2 comes here. See, 2 comes here means A is no more an odd number. We have assumed that A is an odd integer. So, A is equal to 6q is not possible because here 2 comes means it is not an odd number. Now 6q plus 1, yes. See, 6q plus 1 can be odd. Now the next option is A is equal to 6q plus 2. See, here I can take 2 outside because 2 is a common factor here. Inside the bracket I will get 3q plus 1. What does that mean? 2 comes here means 2 into any number. Means that is an even number. It is against our assumption. In the beginning itself we assume that A is an odd integer. So we cannot take this. What about this? Here it is possible. See why? I can take 3 outside here. Okay, inside the bracket I will get 2q plus 1. See, here 2 is not there means it is not even, it is odd. So this is there. Now 6q plus 4, I can take 2 outside. Inside the bracket I will get 3q plus 2. See, here 2 into a number means this is not an odd integer. It is against our assumption. This one also an odd one. Okay, so which are the correct one? A is equal to 6q plus 1, A is equal to 6q plus 3, A is equal to 6q plus 5. These three are the correct options. See, so we have proved that any positive odd integer can be represented as 6q plus 1, 6q plus 3 or 6q plus 5. We can write it like this. Assume A is an odd integer, then we will divide A by 6. We will get a quotient here and remainders as 0, 1, 2, 3, 4, 5. Then we can write A as like this. A is equal to 6q plus 0 is equal to 6q is equal to 2 into 3q. That means A is even. See, here 2 comes as a factor means A is even. Next option is A is equal to 6q plus 1. Okay, that is taken. A is equal to 6q plus 2. What happens? 2 can be taken here. That means A is even. Next step, A is equal to 6 cube plus 3. Next option. That is possible. Next one, A is equal to 6 cube plus 4. Here also we can take 2 outside. That means A is even. And the last option is A is equal to 6 cube plus 5. So we got 3 things as true. So any positive odd integer is of the form 6 cube plus 1, 6 cube plus 3 or 6 cube plus 5. This is our third question. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? Okay, we have two groups here. One having 32 people and the other one 616 people. Okay, we have to arrange them in such a way that, see, they will move in the same column. Okay, for example, if we take here two columns here, means in one column we can keep 16 and in the other again 16. 16 plus 16, 32. Here also we can arrange them in two columns. 16 can be divided by 2. That means 3, 0, 8 people will be in one column and 308 in the other one. Like that we have to arrange them in such a way that they are moving with the same number of columns. Here what is asked, what is the maximum number of columns in which they can march? That means maximum number of columns means here what is 2 actually? 2 is a factor of 32. 2 columns means 2 is a factor of 32 and 2 is a factor of 616. Maximum number of columns means we have to find the highest common factor. Highest common factor of 32 and 616. So we will use, we can adopt any method because in this question no method is mentioned here, right? Any method we can choose. Anyways, let us do it with Euclid's division algorithm. 32. Okay, 616 when divided by 32. Here 1, 32, 9, 2. Then 6. Okay, 32 plus 32, 64. We are going to add it continuously. By adding 32 continuously, I reached 288, which is very close to 296. Okay, so we can take 288 here. How many 32s? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 times. Okay, here the remainder is 8. Now one more thing is there. 32 is there and 296. 32 into something should go near 296. Okay, how we got this 9 here? By adding it continuously, or we can adopt another method. 32 into 10 is 320, right? 32 into 10 is 320. See, 396 is just below 320, right? 296 is just below 320. So just we can multiply 32 by 9. Okay, like that we will get 288 itself. Okay, you can choose this method or this method. Anyways, we divide it like this and remainder is 8. Then what we will do? We will divide 32 by 8. 32 divided by 8 4 times. So remainder is 0. So what is the HCF here? 8. So maximum number of columns here in this question is 8. That is HCF of 32 and 616. This is our fourth question. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. See, this question is almost similar to the second question of the same exercise. Okay, first we will assume that a is any positive integer. See why we have taken it positive integer? See here it is given. For any positive integer, the square is either of the form. So we have assumed that a is a positive integer. Then what is the next step? We will divide a by 3. Why we choose this 3? See, we have to prove it is of the form 3m or 3m plus 1. That is why we choose 3 here. A is a positive integer. When it is divided by 3, what will happen? We will get a quotient. Q represents the quotient and R represents the remainder. As in the second question, we have explained, no, the remainder will never exceed the divisor. The remainder will never exceed the divisor, means remainder can be 0 or 1 or 2. Okay, so we can represent A as like this. A is equal to 3Q, where Q is this quotient. 3Q plus 0, that is 3Q itself. 3Q, or A is equal to 3Q plus 1, or A is equal to 3Q plus 2. These three are the possibilities. Okay, now what we will do? We will take each and every one, because each and every one at a time, only one at a time. See, here we have to prove the square of this. The square of this. So we will take case 1 like this. Case 1 is equal to 3Q. Okay. Now we have to do the square. We have to find the square of this 1. A square is equal to 3Q the whole square. That is 3 square Q square. Okay. 3 square Q square. And here we will get it is as 9Q square. And 9 is a multiple of 3, right? So 3 into 3Q square. Okay. See, 3Q square is an integer, right? Q is the quotient here. So Q square into 3 is another integer. So we can take it as 3m, where m is some integer. M is some integer. Okay. So we got, in first case, the square of any positive integer can be represented as 3m. Now we consider this situation, 3Q plus 1. If A is 3Q plus 1, what will happen? 3A square will become 3Q plus 1 the whole square. Okay, we know the identity. A plus B the whole square is equal to A square plus 2AB plus B square. So what will be 3Q plus 1 the whole square? See, 3Q plus 1 the whole square. See, here in place of A we have 3Q. So 3Q the whole square plus 2AB. In place of B we have 1. 2AB plus B square. B square is, here it is 1. So 1 square. That is 9Q square. 3 square is 9 and Q square. Plus 2 into 3, 6 into 1, 6. 6Q plus 1. Right? So I can write it like this. 9Q square plus 6Q plus 1. See here, 3 is a common factor for these two terms. So I am taking 3 outside. Here I will get 3Q square. Inside the bracket, I got 3Q square plus 2Q and plus 1. Here, Q is the quotient which we got here, right? So, 3Q square plus 2Q, this one can be taken as any integer. So, we can write it as 3m plus 1. Where m is an integer. Here in case 1 m was 3 3q square. In case 2, m is 3q square plus 2q, which is another integer. Okay, now we will take case 3. In our third case, what was a? A is equal to 3q plus 2. So what is a square? 3q plus 2 the whole square. Okay, so we will get 9q square plus 6q plus 4. Okay, anyways, in the question what we have? 3m or 3m plus 1. 3m or 3m plus 1. So we need a plus 1 here, right? So I'll write it like this: 6q plus 3 plus 1. Why split it like this? See, in our question we need it. See, here in the question we have to prove it as 3m or 3m plus 1. Anyways, we cannot take it as the whole thing cannot be represented as a multiple of 3. That is why I took plus 1 here. Okay, now from this part, what we can take commonly? Yes, we can take a 3 here. What is left here? 3q square, 2q plus 1. And again this plus 1. So what is this? Q is the quotient which we got from here. So this is another integer. So we can write it as 3m plus 1. See, 3m plus 1. In this case, m is 3q square plus 2q plus 1. This thing is considered as m, where m is an integer. So what we can conclude? See, any positive integers square can be considered as 3m or 3m plus 1. See, here and all we can represent it as 3m or 3m plus 1, where m is just an integer. This is the last question of our exercise. Use Euclid's division lemma to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8, where m is any integer. This same question can also be asked like this. If n is a positive integer, then prove that n cube can be expressed as 9m, 9m plus 1 or 9m plus 8. Okay, this is similar to the previous question. First of all, we will take a as a positive integer. Okay, what is the next step? We have to divide this a by what? Here we have to prove 9m, 9m plus 1 or 9m plus 8. See, we have to divide it by 9, right? Then what will come as the remainder? 0, 1, 2, 3, etc. up to 8. Right? So we can represent, see, anyways a q quotient will be there. A can be represented as 9q plus 0, 9q plus 1, 9q plus 2, like that. So many options are there. So it is very difficult to do that, right? So what we will do? See, a number which can be divided by 9 can also get divided by 3. See, 27, let us take as an example. 27 can be divided by 9, right? 27 can also be divided by 3. Okay. Another example, 99 can be divided by 9. 99 can be divided by 3 also. So what is the best option here? Let us divide this a by 3. Okay. So we will reduce the number of options or number of cases we have to consider. Okay. Here the remainder can be 0, 1 or 2. Right. So a can be represented as 3q plus 0. That is 3q itself. Or a can be taken as 3q plus 1, or a can be taken as 3q plus 2. Okay, we got only 3 cases now. Okay, Next step is case 1, case 2 and case 3, taking all these options separately. First option is AC equal to 3Q. Here we have to prove what something about the cube of the number, cube. Okay, so A cube is equal to 3Q the whole cube. That is same as 3 cube. This is rules of exponents. We have learned it earlier, no? 3 cube into Q cube. 3 cube is 27. So we got it as 27 Q cube. Actually what we have to prove, same as 9m or 9m plus 1 or 9m plus 8. That means we have to take a 9 outside from here. So 9 into what? 3. 9 into 3 we will get 27. So this is same as 9 into 3Q cube. So it can be considered as 9m, where in this case m is 3Q cube, just an integer. Okay. So we have concluded that case 1, that is the cube of an integer can be represented as 9m. Okay. Now we are moving to the second case, case 2, where A is 3Q plus 1. 3Q plus 1. So A cube is equal to 3Q plus 1 the whole cube. Okay, we have learned the expansion of A plus B the whole cube. A cube plus B cube plus 3AB into A plus B. Right? So here in place of A we have 3Q and in place of B we have 1. So this is 3Q the whole cube plus 1 cube. See, A cube plus B cube is already done. Then 3AB will be 3 into 3Q into 1. A plus B 3Q plus 1. Okay. Now this is equal to 27Q cube. Right? 3 cube is 27 and Q cube plus 1 cube is 1 plus 3 into 3. What is 3 into 3? 9. 9Q into 3Q plus 1. Okay. We have to open this bracket. So we will get 27Q cube plus 1 plus, see, before opening the bracket itself we can do it like, or you can proceed like this also. Okay, we can open the bracket and then summarize. See, I am going to conclude it by here itself. Why? We need a 9 outside, right? We need a 9 outside and plus 1 is also possible. See, here I got a plus 1 and for the rest of the terms I have a 9 in common. Okay, so I am going to summarize from here itself. Okay, I'll just arrange it like this. 9Q into 3Q plus 1, then plus 1. This plus 1 I wrote it here. Okay. In the next step, I am going to take a 9 outside from these two terms. So inside I have 3Q cube plus Q into 3Q plus 1. See, I have used a square bracket. Okay. Then a plus 1 is there outside the bracket. What is this? See, Q is the quotient which we got here, right? So this term represents just an integer. So this can be taken as 9m plus 1, where in this case m is 3Q cube plus Q into 3Q plus 1. Okay, anyways, we could represent the cube of a number like 9m plus 1. Okay. So, what we have concluded from case 1 and case 2? An integer, the cube of any positive integer is of the form 9m and 9m plus 1. Okay, now we are going to consider the third case. In third case, we will take a as 3 cube plus 2. Okay, so what is a cube? 3 cube plus 2 the whole cube. We will use the identity here. So 3 cube the whole cube plus 2 cube plus 3 into 3 cube into 2 into 3 cube plus 2. Okay. Now this is same as 27 cube plus 2 cube is 8 plus 9 into 2 18 cube into 3 cube plus 2. Okay. Now let it be like this, because see, we have a plus 8 here. Question also we have a plus 8 term here, right? And from this term and this term we can take a 9 outside. So what is left here? 9 into 3 cube. See, I have taken a 9 from here plus. Next I am going to take this term. 9 taken out means 2 is left. 2 cube into 3 cube plus 2. See, I have used a square bracket. Then what is left? This plus 8. See, q is the quotient, means this itself is a integer. So this is 9m plus 8. See, here m is 3 cube plus 2 cube into, we have to mention it here, 2 cube into 3 cube plus 2. Okay. Anyways, from these three cases, what we can conclude, the cube of any positive integer is of the form 9m plus 1 or 9m plus 8. Thus, we have done all the exercise problems of exercise 1.1. Hope all of you could understand. Thank you.